Hello and welcome to another video. Today in this video I'm going to talk about how to make custom layers and train them in Tensorflow. Entire source is published online and with explanation. Please check the link below in description. This tutorial shows you how to train a machine learning model with a custom training loop to categorize penguins by species. In this notebook, use Tensorflow to accomplish the following. Import a dataset. Build a simple linear model. Train the model. Evaluate the model's effectiveness. Imagine you are an ornithologist seeking an automated way to categorize each penguin you find. Machine learning provides many algorithms to classify penguins statistically. For instance, a sophisticated machine learning program could classify penguins based on photographs. The model you build in this tutorial is a little simpler. It classifies penguins based on their body weight, flipper length, and beaks, specifically the length and width measurements of their culmen. There are 18 species of penguins, but in this tutorial you will only attempt to classify the following 3. Chinstrap penguins, Jinta penguins, Adelie penguins. Fortunately, a research team has already created and shared a dataset of 334 penguins with body weight, flipper length, beak measurements, and other data. This dataset is also conveniently available as the Penguins Tensorflow dataset. Install the TFDS Nightly package for the Penguins dataset. The TFDS Nightly package is the nightly released version of the Tensorflow datasets, TFDS. Then select Runtime Restart Runtime from the Collab menu to restart the Collab runtime. Do not proceed with the rest of this tutorial without first restarting the runtime. Import Tensorflow and the other required Python modules. Import Tensorflow and the other required Python modules. The default Penguins/process Tensorflow dataset is already cleaned, normalized, and ready for building a model. Before you download the process data, preview a simplified version to get familiar with the original Penguins survey data. Download the simplified version of the Penguins dataset, Penguins/simple, using the Tensorflow dataset's tdfs.load method. There are 344 data records in this dataset. Extract the first 5 records into a data frame object to inspect a sample of the values in this dataset. The numbered rows are data records, one example per line, where the first 6 fields are features. These are the characteristics of an example. Here, the fields hold numbers representing penguin measurements. The last column is the label. This is the value you want to predict. For this dataset, it's an integer value of 0, 1, or 2 that corresponds to a penguin species name. In the dataset, the label for the penguin species is represented as a number to make it easier to work with in the model you are building. These numbers correspond to the following penguin species. 0. Adelie penguin. 1. Chinstrap penguin. 2. Jinta penguin. Create a list containing the penguin species names in this order. You will use this list to interpret the output of the classification model. Now, download the pre-processed penguins dataset, penguins/processed, with the TFDS load method, which returns a list of TF data dataset objects. Note that the penguins/processed dataset doesn't come with its own test set, so use an 80:20 split to slice the full dataset into the training and test sets. You will use the test dataset later to verify your model. Notice that this version of the dataset has been processed by reducing the data down to 4 normalized features and a species label. In this format, the data can be quickly used to train a model without further processing. You can visualize some clusters by plotting a few features from the batch. A model is a relationship between features and the label. For the penguin classification problem, the model defines the relationship between the body mass, flipper and culmen measurements and the predicted penguin species. Some simple models can be described with a few lines of algebra, but complex machine learning models have a large number of parameters that are difficult to summarize. Could you determine the relationship between the 4 features and the penguin species without using machine learning? That is, could you use traditional programming techniques, for example, a lot of conditional statements, to create a model? Perhaps, if you analyze the dataset long enough to determine the relationships between body mass and Kalman measurements to a particular species. And this becomes difficult, maybe impossible, on more complicated datasets. A good machine learning approach determines the model for you. If you feed enough representative examples into the right machine learning model type, the program figures out the relationships for you. Next, you need to select the kind of model to train. There are many types of models, and picking a good one takes experience. This tutorial uses a neural network to solve the penguin classification problem. Neural networks can find complex relationships between features and the label. It is a highly structured graph, organized into one or more hidden layers. Each hidden layer consists of one or more neurons. There are several categories of neural networks, and this program uses a dense, or fully connected neural network. The neurons in one layer receive input connections from every neuron in the previous layer. For example, Figure 2 illustrates a dense neural network consisting of an input layer, two hidden layers, and an output layer. When you train the model from Figure 2 and feed it an unlabeled example, it yields three predictions: the likelihood that this penguin is the given penguin species. This prediction is called inference. For this example, the sum of the output predictions is 1. In Figure 2, this prediction breaks down as 0. 0.2 for Adelie, 0. 95 for Chinstrap, and 0. 0.3 for Gentoo species. This means that the model predicts, with 95% probability, that an unlabeled example penguin is a Chinstrap penguin. Create a model using Keras. The Tensorflow tf.keras API is the preferred way to create models and layers. This makes it easy to build models and experiment, while Keras handles the complexity of connecting everything together. The tf.keras sequential model is a linear stack of layers. Its constructor takes a list of layer instances, in this case, two tf.keras.layers, dense layers with 10 nodes each, and an output layer with 3 nodes representing your label predictions. The first layer's input_shape parameter corresponds to the number of features from the dataset and is required. The activation function determines the output shape of each node in the layer. These nonlinearities are important. Without them, the model would be equivalent to a single layer. There are many tf.keras.activations, but ReLU is common for hidden layers. The ideal number of hidden layers and neurons depends on the problem and the dataset. Like many aspects of machine learning, picking the best shape of the neural network requires a mixture of knowledge and experimentation. As a rule of thumb, increasing the number of hidden layers and neurons typically creates a more powerful model, which requires more data to train effectively. Let's have a quick look at what this model does to a batch of features. Here, each example returns a logit for each class. To convert these logits to a probability for each class, use the softmax function. Taking the tf.math.argmax across classes gives us the predicted class index. But the model hasn't been trained yet, so these aren't good predictions. Training is the stage of machine learning when the model is gradually optimized, or the model learns the dataset. The goal is to learn enough about the structure of the training dataset to make predictions about unseen data. If you learn too much about the training dataset, then the predictions only work for the data it has seen and will not be generalizable. This problem is called overfitting. It's like memorizing the answers instead of understanding how to solve a problem. The penguin classification problem is an example of supervised machine learning. The model is trained from examples that contain labels. In unsupervised machine learning, the examples don't contain labels. Instead, the model typically finds patterns among the features. Both training and evaluation stages need to calculate the model's loss. This measures how off a model's predictions are from the desired label, in other words, how bad the model is performing. You want to minimize, or optimize, this value. Your model will calculate its loss using the tf.keras.losses. Sparse categorical cross-entropy function, which takes the model's class probability predictions and the desired label, and returns the average loss across the examples. Use the TF gradient tape context to calculate the gradients used to optimize your model. An optimizer applies the computed gradients to the model's parameters to minimize the loss function. You can think of the loss function as a curved surface, refer to Figure 3, and you want to find its lowest point by walking around. The gradients point in the direction of steepest descent, so you'll travel the opposite way and move down the hill. By iteratively calculating the loss and gradient for each batch, you'll adjust the model during training. Gradually, the model will find the best combination of weights and bias to minimize the loss. And the lower the loss, the better the model's predictions. Tensorflow has many optimization algorithms available for training. In this tutorial, you will use the tf.keras optimizers (SGD) that implements the stochastic gradient descent (SGD) algorithm. The learning_a parameter sets the step size to take for each iteration down the hill. This rate is a hyperparameter that you'll commonly adjust to achieve better results. Instantiate the optimizer with a learning rate of 0.